These are your video notes for water, bonds, and pH. This covers chapters 2 through 4 in your book, and will be a pretty quick review of some basic chemistry concepts from the last time you took chemistry, either last year or perhaps the year before. So we'll start with the most common atoms in organisms in biology, and not quite sure how to make this box go away, but for us, in this course, that will be carbon, hydrogen, and oxygen. Those are the main three. You might refer to those as CHO. You might have referred to them in the past as CHO. And the remaining three are nitrogen, phosphorus, and sulfur. And as a set of six, these are the most common. You have others. You have, trace metals and other things, but these are the most common that we'll talk about. So let's look at oxygen. Oxygen has an atomic number of 8, which means it has 8 protons. Remember, those protons are kept in the nucleus. It has 8 electrons. Those electrons orbit around the nucleus. And it has 8 neutrons that, along with the protons, live in the nucleus. And I want to focus on the electrons here because the number of electrons kind of is going to determine how these atoms want to bond to other atoms. So these 8 electrons exist in 2 shells. You might remember these shells from chemistry. This first kind of electron shell or electron cloud has 2 electrons in it. And that satisfies, I'll put a little check mark, it's kind of hard to see, that satisfies that first shell. The second shell has the remaining 6 electrons. So 1, 2, 3, 4, 5, 6. And this second shell is the outer shell. And outer shells, in this case, the inner shell is actually perfectly happy with 2 electrons, and we've satisfied that. But this outer shell would honestly prefer to have 8. So this outer shell with its electrons is sometimes referred to as the valence shell, or the valence electrons, or the electrons in that outer shell. And right now, oxygen only has 6 electrons in its outer valence shell. So it's missing, quote unquote, 2. And that's going to be important when we talk about bonds, which means, and I kind of drew these outer shell electrons as pairs. So there's a pair of 2, a pair of 2. It can handle 2 more electrons. It can handle an electron here, and it can handle an electron here. And I apologize for the contrast. It is kind of hard to see. But that means that oxygen can form 2 more bonds. Oxygen can form 2 more bonds. If those bonds are formed with hydrogen, it'll actually make a water molecule. We'll skip hydrogen for now. Let's go down to carbon. Carbon has 6 protons, an atomic number of 6. So 6 protons, 6 electrons, and it can actually have 6, 7, or 8 neutrons, depending on if it's carbon 12, 13, or 14. You might remember that those are referred to as isotopes, right? The number of neutrons changes, but it's all carbon because that's based off the proton count. So these are all isotopes of each other, and actually we use carbon-14 to radiometrically date things because that's an unstable isotope, but those are all called isotopes. And let's take a look at the distribution of electrons in carbon. So per usual, that inner shell, so here's the nucleus here in the center with all the neutrons and the protons. This inner shell has 2 electrons and it's happy, so it is full. The second shell has the remainder, in this case, the remaining 4 electrons. So 1, 2, 3, 4. Well, we know that this valence shell, this outer shell, likes to have 8, right? 2 for the first, 8 for the second. But we're only halfway there, right? We only have 4. So carbon can handle 4 more electrons. This E with the little negative sign is the annotation or whatever for electrons. It can handle 4 more electrons, and therefore it can handle 4 more chemical bonds in general. right? It can handle 4 more bonds. All right, let's go back and look at hydrogen. So hydrogen only has 1 proton, it has 1 electron, and has absolutely no neutrons. So it's a proton being orbited by an electron. So what happens if hydrogen loses its electron? Right? What if we just plucked this electron off and you just have the hydrogen, or you just have the proton in the center, right? What are you left with? You're left with a proton. So when hydrogen loses an electron, it becomes a rogue proton. You might see this referred to literally as the word proton, or H+. H+ is the same thing, it's just a proton. You might also see this referred to as an H ion. All right, so 3 ways to say the same thing: proton, H+, or an H ion. All right, I'm going to skip the rest of these. Let's go ahead and answer this question here. What makes a bond? Right, well, the sharing of electrons. The sharing of electrons. Every time you share an electron, you form a bond. Depending on the atom, that's either going to be with the inner shell, which needs 2 electrons to be satisfied, or 8 electrons in this second shell. And we're only focusing on these 2 kind of shells of electrons because these are the primary and predominant atoms in organisms in biology. I know that other atoms have much more shells, and there's all these different ways to annotate or denote that, but those are not common in organisms, so we really only focus on these 2 shells. And again, these are either the valence shells, or the valence shell is the outer shell. So the valence shell in hydrogen is actually going to be the one with only 2 electrons, but the valence shell in something like nitrogen is going to be the one with 8. And depending on how many electrons are needed in that valence shell, that's going to dictate the types of bonds and the number of bonds formed, etc. So types of bonds in biology, all the ones that we've kind of been talking about so far are called covalent bonds. When atoms share their electrons, not covalence, just covalent, those are called covalent bonds, the sharing of electrons. These are the strongest bonds in biology, which is not what you've learned in chemistry. In chemistry, the strongest bonds are ionic bonds, and that's when you have a transfer of electrons. One atom kind of gives its electron to the other. And in biology, these are actually weak. They're weak because most solutions in your body are water. Your cells or your cytoplasm is between 70-90% water, or 90% water, and your body is 70% water overall. Water takes apart these ionic interactions pretty deftly, whereas it doesn't with covalent, and we'll see that in a second. But ionic bonds are weak. I'm kind of babbling and rambling here, but ionic bonds are weak in biology. Covalent bonds are strong in biology. Let's go to the next one. All right, so that does lead us into a discussion of water. Remember that water is an oxygen and 2 hydrogens. The oxygen, again, has 8 protons, and the hydrogens have 1 proton each. And I'm going to color the electron coming from the hydrogen here right now. So let's say that electron right there is coming from this hydrogen. And this electron right here is coming from this hydrogen. All right, so that takes care of the electrons from hydrogen. Let's go ahead and map out the electrons from the oxygen. So this inner ring, I don't know how to get rid of this box, but this inner ring has 2 electrons, so that inner ring is satisfied. And then we have 6 electrons left over, and I'm just going to kind of put them, let's do 1, 2, 3, 4, 5, and I'll circle this. and 6, and I'll circle that. And I'm circling that because the oxygen and the hydrogen are sharing the electrons here. Actually, I'll circle both of these, right? So hydrogen's inner shell, which has 2 electrons, is now satisfied. And same thing with this hydrogen over here. And oxygen's outer shell, which needs 8 electrons, is also satisfied. So this is a completely satisfied molecule. All the atoms are happy, their valence shells are full, and the type of bond that this is, because the electrons are getting shared, is called a covalent bond. So water actually has 2 covalent bonds, one for each hydrogen. So that is a covalent bond over here as well. All right, the sharing of electrons is not exactly even. Oxygen does not share well. It tends to be an electron hog or an electron sucker. The more technical term for that is to say oxygen is electronegative. Negative, and you might have remembered that from chemistry. I don't need that E there because I wrote it here. So oxygen is an electron, I'll say this in the not scientific way. Oxygen is an electron sucker. Whenever you see oxygen, I want you to think it's going to hog the electrons. It's going to suck the electrons. Think of it like this. Oxygen has 8 protons. The hydrogens only have 2. This is a very uneven tug of war. Right? 8 versus 2. Oxygen is going to win that fight. Its 8 protons hold on to those electrons tighter. So those electrons, yes, they're being shared with hydrogen, but they're being much closer held to the oxygen. And what that does, whenever you pull electrons toward yourself, that's going to make you more negative, right? So the oxygen actually becomes slightly negative. I'm trying to make a negative sign. It just looks like a mess. That's a big negative sign. And the hydrogens, which, yes, they're sharing the electrons, but the electrons aren't really spending that much time around them. So the hydrogens become slightly positive. And you might see, like in the textbook or something, this little S-looking thing. That's sigma. That means partial. So you have a partial positive charge by your hydrogens, and you have a partial negative charge by your oxygen. And that's kind of what this image here is showing. You've got your partial negative by your oxygen, and you've got your 2 partial positives by the hydrogen. And these arrows are just showing you that the electrons are kind of being held more closely by this oxygen atom than by these 2 hydrogens. And what that does is it gets you what we call this a little Mickey Mouse diagram. The hydrogens and the side of the molecule with the hydrogens has this positive side, and the side of the molecule with the oxygen has this negative side. And whenever you have an uneven distribution of charges, where the positives are kind of one area and the negatives are on the other area, that is called a polar molecule. It's just like a magnet. Like a magnet might have a positive side and a negative side, right? Same thing with water, right? It has a positive side where the hydrogens are and a negative side where the oxygen is. So that is a polar molecule. It is important to note that the overall charge is neutral. The overall charge is neutral, is a 0 overall charge for a given water molecule. But within that water molecule, there are areas of positiveness and areas of negativeness. So that's why we call it polar. One important property of being polar is that you are hydrophilic. So if we're going to split this word in half, hydro obviously is referring to water, and philic means to love. So if you are hydrophilic, that means you are attracted to water. And actually, anything that's polar is going to be attracted to anything else that's polar, because if you have a partial positive, if there are any partial negatives out here, they're going to want to attract, right? If there are any partial positives out here, the oxygen's going to want to attract. So polar molecules attract and stick to other polar molecules. Those are called hydrophilic molecules, and water is very, very hydrophilic. It actually will stick to itself all the time. That's cohesion. We'll talk about that in a second. Let's take a look at carbon, which in this case here is a methane molecule, CH4. Carbon's also one of the primary atoms that builds bodies and lipids and carbohydrates, etc. So this here is a carbon atom with its 6 protons, and remember it has 6 electrons, so we'll draw 2 of those electrons in this inner ring, and the other 6 are going to be on this outer ring. We've got 1, 2, 3, 4. Oh, I'm sorry. The remaining 4 of the 6 are on the outer ring, and the hydrogens bring their own. So that electron there is from a hydrogen. That is from the hydrogen, that's from the hydrogen, and that is from the hydrogen, right? So all in all, the hydrogens have their electrons, their shell satisfied. They only need 2, and the carbon has its 8. So this is a happy, satisfied molecule. But let's look at the tug of war between the protons. In this case, carbon is bringing 6, and the hydrogens as a set, 6 versus 4. 6v4 is a much more even fight than 2v8 here. So the electrons are going to essentially be right in the middle, if you want to think of it that way. They're going to spend their time kind of equidistant between the hydrogens and the carbon, between the nuclei of those 2 atoms. Which means you're not going to have these regions of positive and negative area. So this molecule is called a neutral molecule. The overall charge, yes, is also 0, just like water, but within that molecule there are no areas that are more positive or negative than other areas. So this is called a non-polar molecule. A non-polar molecule. And before I forget, what type of bonds actually hold the hydrogen to the carbons? The same type of bonds up here. These electrons are all being shared. These covalent bonds are called non-polar covalent. So there's categories of covalent bonds. So if we look at water, what type of covalent bond is this? This is called a polar covalent bond. So polar molecules have polar covalent bonds. Non-polar molecules have these non-polar covalent bonds. All right, non-polar molecules are called hydrophobic. Hydro is water again, and phobic means to be afraid of, or to fear, or to not want to have anything to do with. So fear, but basically these are not going to bind to polar molecules. Think of other things that are polar, or that are non-polar, I'm sorry. What else besides methane is non-polar? The quintessential typical thing you might think of is oil, right? Oils. Olive oil, canola oil, motor oil, right? They don't tend to mix well in water. And if you think of the structure of these, which we'll talk about later this week, oils are comprised of mostly carbons and hydrogens. And we know, in this example with methane, that there's no polarity between carbons and hydrogens, which is why they don't mix well in water. So these are non-polar covalent bonds. They are hydrophobic. All right, so in general, when you look at a molecule, a picture, how would you know kind of instantly if that molecule is hydrophilic or hydrophobic, right? And what are some characteristics? Well, if it's hydrophilic, we know that it's polar, and we know that it likes water. So I'll put a check mark, water. It likes water. But how would you know, right? How would you know by looking at something? If it has OHs, it's a polar hydrophilic molecule. It means it at least has regions. Remember, the oxygen is slightly negative and the hydrogen is slightly positive, right? The oxygen is not sharing these electrons evenly. So every time you see a hydroxyl group, an OH group, remember this is called a hydroxyl, you might remember that from chemistry, that's an indicator that you're looking at a polar molecule. How would you know about hydrophobic? Well, we know it's nonpolar. We know it doesn't like water. I'll do X water. But what would give it away, right? Well, the absence of hydroxyl groups, but also the presence of carbon-hydrogen bonds. Remember, just like in methane, which is why we talked about it, carbon-hydrogen bonds are non-polar bonds. So that's kind of the indicators to look for when you're trying to figure out the behavior of a molecule. And this is going to be an important concept that comes up over and over and over again. And remember that these types of bonds are very common in oils, which by experience we know does not dissolve well. No dissolve in water. All right, this also gets us some other properties of water. Polarity really gets us all the properties of water. So if you have a cup or whatever, all these water molecules, which I kind of have drawn out here, the partial negative charge of the oxygens are going to be attracted to the partial positive charge of a hydrogen of a different water molecule, right? Of a different water molecule. So you're going to have an attraction here that I'm going to draw with a dotted line. You'll have an attraction here. You can pause the video and kind of finish this out, but draw as many lines here as you can. So take a second and do that. All right, hopefully you've had a chance to do that. Let me go ahead and finish drawing some. You might have an attraction here, an attraction here, an attraction here. But what I want you guys to remember, or maybe you kind of have relearned this, is that one hydrogen can only form one bond. This is actually called a hydrogen bond or an H bond, right? The oxygen can actually form two, right? So you shouldn't have something like this, right? Because now this hydrogen has a H bond twice. It has two H bonds. It can't handle that. It doesn't have enough valence electrons for that. So hydrogens can handle one, the oxygens can handle two. So how many total hydrogen bonds can be formed with a single water molecule? How many hydrogen bonds can a single water molecule be engaged in, right? The total number is 4 per water molecule, right? 2 for the slightly negative oxygen, and then 1 each for the slightly positive hydrogens, right? So the hydrogen bonds are formed between areas of polarity of two different molecules, This property is called cohesion, right? Water sticking to itself. And it's a direct result of its polarity. If you have something like glass, so there's a piece of glass here, that has an uneven distribution of charges, which glass does. It has areas that are slightly positive and negative, kind of all scattered all around it. You'll have the positive hydrogens want to attract to those negative regions, and the negative oxygens will want to attract to the positive regions. This is why when it rains and you're in a car, some of the smaller raindrops, if they're not being overwhelmed by the pull of gravity, will stick to the window. This is called adhesion. This is water sticking to something else that's polar, but it's just not water. So this is water sticking to something else. Water sticking to something else. That is also polar. The combination of cohesion, cohesion really, not adhesion. Cohesion also leads to another property called surface tension. If you have a cup of water or like a swimming pool that has a very still surface and you like belly flop into it, it hurts, right? It hurts because the water molecules at the surface are kind of pulling on each other, creating like a tension, like a skin almost on top of the water that's difficult to break unless you kind of puncture it. So that's surface tension. It's a property of water resulting from the polarity of it, and it's kind of cohesion in action. All right, if you combine cohesion and adhesion, you get what's called capillarity or capillary action. So capillary action is when you have, usually it's a very, very thin tube. Sometimes they're made of glass, but they don't have to be. It can be a straw or something thin like that as well. It could be the xylem and phloem in plants, if you remember that from freshman bio. But basically very, very thin tubes. If you have kind of a cup or a tub of water here, and you put the tube in the water will move up the tube beyond the initial level of water because the water is basically climbing up the sides because it's attracted to the positive and negative charges in that material. So a combination of adhesion and cohesion is actually going to pull that water up the tube, and you can actually color like flowers with this. You can put flowers in colored water and the petals will turn whatever the color of the water is because the water is moving up the stem, and that's made of very, very thin tube material. So we actually never defined an H bond, so let's go ahead and define it, and I think I can actually type this out. Probably should have been doing this the whole time. But an H bond is a bond between slightly positive atoms and a slightly negative atom of a different molecule, and that's key. They are not in the same molecule. In biology, the slightly positive atom is usually the hydrogen. That's why it's called a hydrogen or an H bond. The negative atom is usually oxygen or nitrogen. It is, in chemistry, sometimes includes fluoride to make fluoride or derivatives of it, but not too common in bio. It's usually oxygen or nitrogen. All right, how do we break hydrogen bonds? We use kinetic energy, motion, right? Kinetic energy is heat. So temperature is a measure of kinetic energy, and that's because if you're jostling around all of these, imagine that these water molecules are all holding hands and then there's an earthquake, right? All that energy is gonna kind of break their hands apart. They're not, it's gonna be harder to hold hands. So, right, this constant movement and the more and more of it between these molecules makes it harder to maintain those hydrogen bonds, and that's how they break. And remember that there are 4 hydrogen bonds per water molecule that need to get broken. This is why it takes water forever to boil, because there's a lot of hydrogen bonds there, and that's going to take quite a bit of heat and kinetic energy. All right, water's polarity also makes it a great solvent. So if you're looking at something like sodium chloride salt, which in chemistry is a nice ionic bond example, this actually falls apart because remember, these are very, very weak in biology, and here is why. When you drop sodium chloride or anything that has ionic bonds into water, which in biology is pretty much everywhere. Remember, your cells, cytoplasm is upwards of 90% water. Overall, in like your bloodstream, etc., you know, on average, we're 70% water. So water is the rule in biology. So what water is going to do is separate, no PDA, between the sodium and the chloride ion. What's going to happen here is kind of cool. The negative oxygen is going to orient, or the water molecule is going to orient itself so that the negative oxygen is facing the positive ion, the sodium ion, right? And water is going to orient itself all around here. So the oxygens face the sodium ion because they're negatively charged and they're attracted to that positive, and they completely isolate it. The hydrogens are sticking out here, right? These little small ones are all hydrogens. And they separate it from the chloride ion, right? Well, the chloride ion is kind of the opposite. Here, it's a negatively charged ion, so all of the hydrogens are going to kind of stick to it. It's going to arrange, the water molecule arranges itself kind of the other way. So all your water molecules again kind of surround the chloride ion, and just like over here, they separate it. It's just that the water molecule is oriented so that the charges are attracting to each other. That's how water is a universal solvent. That's the mechanism behind how it dissolves anything that dissolves in water. Again, if you have a polar area, you're going to dissolve in water. All right, next, go through my notes. You might remember that you can deal with concentrations because we're continuing here with water. You did concentrations in chemistry, and you measure concentration using what's called molarity. Molarity is the number of moles of a compound in a 1 liter solution. Remember that a mole, this is the Avogadro's number, what is it, 6.02 times 10 to the 23 molecules. That is quite the number of molecules. So let's say we have 1 mole of glucose. So 1 mole of glucose, so glucose again is C6H12O6, is dissolved in 1 liter, and it's not a liter of water, it's a 1 liter solution. Right, sorry, I'm having issues with my cursor here. And in a 1 liter solution. So how much glucose do you need to put in to this solution if you want 1 mole of molecules in there? So in order to do that, you have to figure out, you have to use atomic mass. So you would say, well, what's the mass of 1 mole, right? Well, carbon, 1 mole of glucose. Carbon there's 6 carbons, 12 hydrogens, and 6 oxygens. The atomic mass of carbon is 12, and there are 6 of those. The atomic mass of hydrogen is 1, and there are 12 of those. And the atomic mass of oxygen is 16, and there are 6 of those in 1 molecule of glucose, which gets you an atomic mass of 180. So this gets us 180 grams. 180 grams of glucose in 1 liter solution, you can cross this off, is a 1 molar solution of glucose. So down here, I have 3 containers. They're all the same size. We have to assume that. That's constant. If you have a 1 molar concentration solution of glucose, look at all this. Right, look at all this glucose that's settled down here. This all hasn't settled, but here it is. The rest is the water. Right? We know that there are 180 grams of glucose, or 6.02 times 10 to the 23 molecules in this 1 liter solution. I want you to pause the video and do the same for the 0.5 molar and the 0.1 molar solutions of glucose. how many grams are there and how many molecules are there in a 0.5 molar solution of glucose. Do the same for the 0.1 molar solution. Unpause the video and see if you got it. All right, here we go. You should have 90, and you should have half of this, which is 3.01 times 10 to the 23. Here you should have 18, that's 10%, and you should have 6.02 times 10 to the 22. All right, let's keep going. You've got glucose stretched out here. Glucose can also be visualized as a ring structure. So these are both glucose, but we'll look here. How do you know if this molecule is polar or nonpolar just on this information here? Pause the video, try to figure it out. All right, hopefully you've done that. This is a polar molecule. Glucose is polar. You can tell because it has OH groups. It actually has quite a few OH groups. Remember that these OH groups scream polarity, right? The oxygen steals, it hogs, it sucks the electrons from hydrogen. It's much more electronegative, so the oxygen is slightly negative and the hydrogen is slightly positive. Everywhere you have that, you're going to have regions of negative and positivity, right? Every single time you have that. That makes the molecule polar, even though the overall charge is neutral. Remember, this is your, before I forget, your OH group is again called the hydroxyl group, and that basically tells you, hey, I'm a polar molecule. All right, last, kind of towards the end here, we do need to review pH because it is a property of solutions, right? In chemistry, you always dealt with the pH of a given solution. Remember that pH is the power or concentration of hydrogen. Remember that this is also just protons. Oops. So the concentration of protons in a solution. It is also the concentration of hydrogen ions, or H ions in solution. It's different ways of saying the same thing. The formula is the negative log, the pH is equal to the negative log of the concentration of protons, or hydrogen ions. Right? So go ahead, break out your calculator. You can pause if you need to go find one. Get a calculator and come back. And here's a little chart, and you can kind of visualize this in kind of three sections. There's this pH, there's this middle section, and there's this scientific notation section. All right. So the scientific notation for 1 molar, you should remember from chemistry, is 10 to the 0 moles, right? Scientific notation for 0.1 molar is times 10 to the negative 1 moles. 0.01 molar is times 10 to the negative 2, right? And so on and so on and so on. So this is negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, and then 0.01 molar is times 10 to the negative 9 molar, right? Which of these has the most hydrogens and which has the least hydrogens? Which molar solution? Hopefully, you're able to identify this first one as having the most hydrogen. And again, of the ones here, times 10 to the negative 9 has the least hydrogen. What is the pH of each of these solutions? And this is where you need your calculator. So go ahead, plug and chug. Find the pH of, let's do 0.1. Find the pH of 0.1 molar. Find the pH of 0.00001 molar, and go ahead and let's do this last one down here. Find those three. Go ahead, pause, and do that. All right, you should have realized that the pH for 0.1 molar is 1. The pH for 0.00001 molar was 5, and this last one down here, the pH was 9. And yep, you are recognizing a trend. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you were able to pick it out, the pH is equal to the exponent over here. It's positive, but it's equal to the exponent. So if you have a solution that is times 10 to the negative 3 molar, you know it has a pH of 3. So nice, easy pattern to remember. You will need it for a lot of the stuff in AP Bio. That's a nice shortcut. All right, last portion here for this section. Water, remember, can be written as a dissociation equation between hydrogen ions and hydroxyl ions. So remember, the pH of water is 7, so the concentration of hydrogen in water is to the negative 7th, and the concentration of hydroxyl is to the negative 7, which means you have a total of 14. And whenever you add these up, you're always going to total up to 14. So if the pH of a solution is 5, POH, the concentration of hydroxyl, OH, is, I can add to 14, is 9, right? If the concentration of OH is to the negative 12, then POH is 12, and we should be thorough. We should put molar here, times 10 to the negative 12 molar, right? If the concentration of hydroxyl is 10 to the negative 12 again, then pH, they have to add to 14, must be 2. And we'll work more on this together. The last little bit here is this couple questions, and then we're done. Do you have hydrogen ions in your body? Right? Do you have protons in your body? Yes, of course you do, right? Your cells have cytoplasm, right? The pH is roughly 7. I mean, the pH of your body as a whole is roughly 7, which means you have times 10 to the negative 7 molar concentration of protons, of hydrogen ions in your body. So yes, you do. So you have 0.0000001 molar. That's actually the specific concentration of hydrogen ions in your body. In the stomach, so we're going to focus on something much more specific, it's pH of about 2, right? So in your stomach, that's going to be a concentration of about 0.01 molar, right? That's times 10 to the negative 2 molar. And obviously there are significantly more hydrogen ions in your stomach because the concentration is much greater and the pH is much lower. Last bit here, and then we're done. Buffers. What do buffers do? I'm not going to go into buffers in too much detail other than to remind you that buffers, and I can type this out, can either donate or remove hydrogen ions or hydroxyls, and that subsequently stabilizes pH, right? So an acid, so hydrochloric acid, HCl, acids tend to donate the hydrogen. So in that case, acids will tend to donate the hydrogen. Bases tend to donate, sodium hydroxide, tend to donate the OH group. And both the hydrogens and the OH group will then go on to react with either OH or hydrogen ion to form water.
All right, so that's how the buffers work in general. I'm not going to go into more detail about buffers than that, but just remember that they either donate or remove hydrogen ion or hydroxyl ions to stabilize pH by reacting with other ions to form water. So that is a quick overview of water chemistry, pH, and bond formation, chapters 2 through 4. I hope this helped, and we will talk more about this together in class. I'll see you then.